Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 7 of a unit Work, Power and Energy. Let's begin with today's session. In today's session, we are going to discuss about the conservative and non-conservative forces, and we are also going to discuss in this session about the equilibrium. So first let's begin with the conservative and non-conservative forces, and then we will switch to the equilibrium. So let's have a look. So one of the forces could be categorized as the conservative forces, and while some other forces can be categorized as the non-conservative forces. So when we discuss about the conservative forces, this depends on the depends on initial position, final position, but not depending not depending on the path to reach final position from initial position. So these are the forces which depends on the initial position. It depends on the final position, but it is not depending on the path to reach final position from the initial position. This forces are the conservative forces, while non-conservative forces, these are the forces which depends on initial position, final position, as well as path taken to reach final position from initial position. So these are the forces which depends on the it depends on the initial, it depends on the final, as well as it is depending on the path taken on the when from where it has been reached from final position to initial position. So this is the basic difference. Now we are going to discuss this forces in more detail. So let's first look at the conservative forces first, and then we will switch to the non-conservative forces. So in conservative forces, work done by the force around a closed path is always zero, and this is, as we have discussed, independent of the path. Such a forces are known as the conservative forces. One more very important aspect is if force can be defined like this: F is equals to minus of du by dx, where du or delta u is the change in potential energy. It's a change in the potential energy, and dx it's a change in position. Yes, so du it's a change in the potential energy, and delta x it's a change in position. So if it has been defined as F is equals to minus of du by dx, then the force is called as the conservative forces. Now which are the forces which can be categorized as the conservative? We understand gravitational forces, elastic forces, electrostatic forces, magnetic forces, etc. This all are the forces which are conservative, as well as this all are the central forces. That means force would be acting from center of one body to center of the another. Yes, this all are the conservative in nature. So this is very important aspect. First you need to always focus on two parts. First, this is the first point where work done by the force around a closed path is zero, and second this, because this relation has only be defined, this relation has only be defined for the conservative forces. We cannot have any relations for the non-conservative forces. I hope this is clear. Is it clear? Is it? Now let's work and look at the non-conservative forces. So in this case, work done by the force around a closed path is not equals to 0, and it depends on the path as well. So when I said it depends on the path as well, as we have discussed, let's look one more time, that it depends on the initial position, it depends on the final position, as well as it depends on the path. So here when I say it depends on the path, I mean to say it depends on the initial and final. That is absolutely okay, because even the conservative forces depend on them. But it depends on the initial, it depends on the final, as well as it depends on the path. Such a force is known as the non-conservative forces. All kind of energy losses forces, such as frictional force, viscous force, air drag, all this kind of forces are considered as non-conservative forces. All these forces are non-conservative forces. I hope this is clear. Now, how could I represent that numerically, that these forces are conservative forces and these forces are non-conservative forces? Let's have a look. Let's suppose the situation is something like this, that this is wedge and this is angle theta. This height h is given, this height h is given, and this is block m. Yes, and this is smooth wedge, this is smooth wedge. That means I can represent it as mu is equals to 0 in this case. So in this situation, when this block reaches over here at the bottom of the wedge, what would be the work done? So in this case, find out work done when when block having mass m reaches to the bottom. So how could I do this? What I understand is that this is the x, which is not being given, but I can consider it for the my reference. It's an x. This force is the mg sine theta. Yes, a normal force would be there, mg would be there, mg cos theta would be there. So if I write down work done due to all the forces, work done due to normal would be equals to 0, because theta is equals to 90 degree. Theta between force and displacement is 90. Work done due to mg cos theta, again it would be a 0. Why? Because theta is equals to 90 degree. We have discussed all these things in the previous sessions. Yes. Now what about the work done due to mg sine theta? I can write like this. It's an force which is mg sine theta multiplied by displacement, and that displacement can be written as x. If I want to replace it, I can replace this according to this. It's a sine theta, that should be is equals to h by x. From this, x is equals to h by sine theta. So this is mg sine theta multiplied by x, and x can be replaced as h by sine theta. So this 2 has been cancelled, and this is mgh. So now what you need to observe, why we are discussing over here is, why we are discussing these things over here is that this was the situation. Look at this and observe this very carefully with respect to conservative and non-conservative aspect. This is height h, this was height h, this was block m, it has reached to here, this is theta. So if I consider it according to the displacement, let's assume that a block was here in the initial situation m, and it has finally reaches to here, and this has been displaced by h height. So in this case we already derived it's a work done is equals to m into g into h, that we have derived in the previous slide. Now if it has been traveled through here and this block has reaches to here, then what I can have is that this is force due to gravity, even this has been the displacement. So here it's a work done, it's equals to m into g into h. So look at this, in one of the situation it has traveled through this path, in another situation it has traveled from this point to this point. Both path are different, but their initial position, look at this, their initial position, even their final position are equal. Yes, even though a situation was something like this, that let's suppose this m is there and it has traveled through this path and it has reaches to here, then even if I calculate the work done, it would be an mgh. So this is how conservative forces behaves. That's why we can say it's the gravitational forces. Gravitational forces are conservative forces. I hope this is clear now, that what exactly conservative forces is all about. Is it clear? Is it? Any doubts? Any confusion over it? Anything? No? Great. Now let's have a look. What could be the situation when we are dealing with the non-conservative forces? Let's suppose again we have taken the wedge. This angle is theta. This height it is h. And here a friction is there. So let's suppose the block was initially at this position and finally it is going to be landed on this. This is the mass m, it is going to reaches over here, and this is the displacement. Again this is not given, I am just considering it for my purpose. This is 90, we always know. Yes, so let's just find it out, that what all forces are being acted on this situation. This is theta. If my block is over here, then let's have all the forces. This is mg sine theta, this is normal, this is force of friction. What else? Yes, mg cos theta. So this all forces are acting. Again I need to do one same thing, work done due to normal, it would be 0. Why? Because theta is equals to 90 degree. Work done due to mg cos theta, it would be again 0. Why? Because theta is equals to 90 degree. Yes, these two forces are 0. Now work done due to mg sine theta, it's a work done due to mg sine theta, that should be is equals to force mg sine theta, displacement x, angle 0 degree, cos 0. So this is equals to mg sine theta multiplied by x. Let's keep it as it is. Now one more thing, even work done due to friction would be there. Friction is acting on the upward side of the wedge, while block has been displaced on the downward side. So if I write work done due to friction, what I need to write is it's a force of friction, which should be a mu mg cos theta multiplied by it has been displaced by x, and angle over here it's a cos 180 degree. So this is equals to cos 180 minus 1. So this is equals to minus of mu mg cos theta into x. I hope this is clear. Is it clear? Is it clear? So if in this situation, I would go for the net work done, this was the case. This was the wedge having a friction mu, and the block was initially here, and it is going to be rich at this bottom, and this is height h. So net work done would be work done due to friction minus my sorry, I need to write it's a work done due to mg sine theta, work done due to mg sine theta minus work done due to friction. So this is mg sine theta into x minus mu mg cos theta into x. So if I replace this, this is theta sine theta could be replaced as h by x. This is equals to mg sine theta multiplied by x. X would be h by sine theta minus mu mg cos theta multiplied by h divided by sine theta. This 2 has gone, and the term that remains is mgh minus of, this is mu mgh into cos by sine, it's a cot theta. So this is not only mgh, it is something else too. So this is how we can say that frictional force is non-conservative in nature. So not only friction, it is the case that at this point of time we understand only the friction. That's why I have taken this case. I have taken this case of friction. Not only friction, but all the forces, all those forces which are there, which are going to lose the energy, which are going to make the loss of energy, all those forces will be in the category of non-conservative forces in nature. So is it clear? Is it any doubts in this? Yes. One more thing. Always keep in mind, this is note, that F is equals to minus of du by dx. This is defined for conservative forces only. This has been defined for conservative forces only. Yes, please do remember this thing. And this is very unique relation, because in the physics of 11th and 12th, this is the only relation which relates force, change in potential energy, and change in position. So this is the unique relation which can relate this three. In the physics of class 11 or in class 12, we are not having any relation which can relate these three terms. So please note this. This is force is equals to minus of del du by dx, and this can be defined for conservative forces only. From this I can have this, it's an du could be written as minus of f into dx, and if I'm going to integrate this, then I can have this change in potential energy should be equals to minus of integration of f dot dx, which can be categorized as minus of work done. I hope this is clear. So please keep in mind that this is possible. This can be used for conservative forces only. If the forces are non-conservative, this is not available at all. I hope this is clear. Is it clear? Great. So any doubts, any concern over conservative or non-conservative forces, any discussion? No? Great. Now let's work for the equilibrium. Now tell me, what is equilibrium according to you? We have already defined it when we are dealing with the laws of motion. What is equilibrium? What is it? When I say equilibrium, one thing that came into my mind is when net force on the system is zero. First thing. A second thing, when net acceleration when net acceleration of the system is zero. So when I said equilibrium, I mean to say this two things: a net force is zero, and if you understand that it's a net force is zero, you must understand that its acceleration must be a zero, because we know from the Newton's second law of motion, sigma f is equals to mass times the acceleration. I hope this is clear. So now here we are going to discuss equilibrium in relation with potential energy as well. So in the equilibrium, in the equilibrium, we are generally going to discuss three equilibriums could be there, but we are going to discuss two equilibriums on a primary basis. One is the stable equilibrium, one is the stable equilibrium, another is the unstable equilibrium, and the one more is the neutral equilibrium. Yes, we have a three equilibriums: stable equilibrium, unstable equilibrium, and neutral equilibrium. So let's check this one by one, and let's have an idea that what is equilibrium. So before we start with the equilibrium, I need to see the graph for potential energy. Shall I write it? Graph for potential energy versus distance. So this is the graph for the potential energy versus distance. Let's have a look very carefully that this is the situation, this is the potential energy, and this is the distance. So when I plot this graph, let's have a look. It is something like this. So if you observe this logically, this is the position. This is the position where potential energy is maximum. Yes, this is the position. This is the position when potential energy is minimum. So these two graphs are there. These two locations are there. At one of the location, potential energy is maximum, and at another location, potential energy is minimum. Okay, this is the situation when potential energy is maximum, is being available when position x is x1, and this is the position when potential energy it's minimum, it's an x2 position. I hope this is clear. Now I have one relation which can relate potential energy, position, or I can say distance. So rather to use a distance, let's use it's a position. So it's a potential energy versus position. So we have one relation which can relate potential energy and position, and which could be given as that F is equals to minus of du by dx. So du by dx is the slope of this graph. Please be very much clear. Please be very much clear with with this graph and with this equilibrium. So du by dx is the slope of this graph. It's a du by dx. This is the slope of given graph. So when I say this is the slope of given graph, at this point and at this point, this is the first location while I say m1, and this is the second location while I say m2. At both the position, slope is 0, and du by dx is equals to force. That means I can say that this both are points of equilibrium. This both are points of equilibrium. While I say both, I am talking about this position as well as this position. So I'm talking about these 2 points where equilibrium would be there. Why equilibrium? Because force is 0. If force is 0, my particle, or I can say about my system, that my system is in equilibrium. I hope this is clear. Any doubts in this? Tell me. Is there anything which is not clear up till now? No? Great. Let's have one step ahead of it. That this was our situation, that this is potential energy, this is position, and this was our graph. Yes, so this is the position, this is the location where PE is maximum, this is the location where PE is minimum, this is the location where potential energy is maximum, and this is the location where potential energy is minimum. So let's understood the situation very quickly. Let's have a snapshot of this situation. Let's have a snapshot of this situation and observe the situation. Let's suppose it is something like this, and I have put certain object over here. So what you need to do is, you need to observe this with the help of u versus x position. Yes. So first, when u versus x is there, you need to access this. Let's look at this. This is an object M, and it has been placed over something like this, maybe certain curvature or maybe certain object. So first thing, displace the object M slightly from its position of equilibrium, from its position of equilibrium. If it can come back to its position by itself, then it is the position of stable equilibrium. It is the position of stable equilibrium. Otherwise, it is unstable equilibrium. Otherwise it is unstable equilibrium. So read this very carefully. We are going to discuss about this. That what you are supposed to do is, first thing you must keep in your mind that this is the case for the potential energy versus distance. What you need to do is displace your object slightly from its position of equilibrium. If after it has been displaced from its position, if it can come back to its original position by itself, you are not going to apply any force, by itself, then it is the position of stable equilibrium. Otherwise it is unstable equilibrium. So let's see this again and again, because stable equilibrium and unstable equilibrium, we are going to discuss it for once only, for 11th class as well as 12th class, and we are going to use these concepts for 11th as well as 12th. So this is the situation. Let's suppose this was the object, and the second situation of equilibrium, it was just the snapshot of this. I'm going to take this situation because this is the location of equilibrium, that this was the situation, and I have put my object over here. So now let's assume that if I have displaced in this case my object from here, let's provide a certain disturbance over here, and it will be moved from its position maybe in negative x or maybe in positive x. So in this case, object cannot come back to original position by itself. So this is the location of unstable equilibrium. While in the second situation, look at that very carefully. Look at this very carefully. If I displace it over here, if I displace it by from here, I have provided a certain disturbance to it, and if I am there to displace it, then it will move on this, then move on this, then move on this, and again at the end of the day, it will reach to its initial position by itself. So object in this situation, object can reach to its initial position by itself. So if object can reach to its initial position by itself, this is the location of stable equilibrium. Please do remember this thing always. But this should be the case, with u versus x. This should be the case with u versus x. How could I check? You do not need to do anything, just see, put the object where they want, that whether it is an equilibrium position or not. Displace your object. Now stand up aside and just try to observe that whether my object is capable enough to come to its initial position by on its own. If answer to this question is yes, then it would be a stable equilibrium. But if answer to this question is no, then it would be an unstable equilibrium. It is as simple as that. One more thing, you can have this concept, you can have this idea from one more point of view, that when it is the case of unstable equilibrium, look at this. So this is the case of unstable equilibrium, and this is the case of stable equilibrium. So look at this one more thing. When unstable equilibrium is there, your potential energy would be maximum. Even this is the concept which you might have discussed in your chemistry classes as well. Yes, so it is the case when you discuss about the unstable equilibrium, your potential energy, your potential energy will be maximum. But and when you are talking about the stable equilibrium, let's have a look. This is the situation of stable equilibrium. So when you look at the stable equilibrium, your potential energy will be minimum. I hope this is clear. Is it clear? So you can have one more idea from this, that if my potential energy is maximum, it must be the position of unstable equilibrium. But if my potential energy is minimum, it must be the position of stable equilibrium. Is it clear? Got it? Are you clear with this? Are you clear with this? Are you sure? Now we have one more approach from the position or the graph of the f versus x. Yes, that they ask one more category of question of equilibriums from the same concept in certain a detailed approach. So let's look at this graph one more time. Yes, this was the situation, this was the position of unstable equilibrium, this was the position of stable equilibrium. Yes, so if I take this position, I must understand that du by dx equals to 0 over here, and from here it is the d square u by dx square, that would be less than 0. And if I take a second differentiation over here, It's a double differentiation, d square u by dx square. At this point it is greater than 0. So now I have the relation which is said as the f is equals to minus of du by dx. From this I can have the relation, it's a df by dx, which could be, I am differentiating it, it's a minus of d square u by dx square. Now understood this very carefully, that this is the position of unstable equilibrium where d square u by dx square is less than 0. So I can say that df by dx for unstable equilibrium should be equals to, as this is less than 0, even this is minus of negative number. Why? Because this is less than 0. So if df by dx for unstable equilibrium should be greater than 0. I hope this is clear. So when I am having a graph of f versus x, when I am having a graph for the f versus x, the slope of this graph, because df by dx is the slope of that graph would be greater than 0. Now one more thing, let's talk about the stable equilibrium. So when I say df by dx is equals to minus of d square u by dx square, and you are saying this, that at stable equilibrium d square u by dx square is greater than 0. So for stable equilibrium d square u by dx square is already greater than 0. So when this term is greater than 0, which is going to be multiplied by negative number, so I can say that df by dx for the stable equilibrium, df by dx for the stable equilibrium is less than 0. So what you need to do is, you need to remember two conditions. One of the condition is this, that df by dx for stable equilibrium is less than 0, while df by dx for unstable equilibrium is greater than 0. Is it clear? Is it clear? Are you clear with stable equilibrium and unstable equilibrium? Have you got it? Are you sure? Yes. So please make a note of this, that if df by dx is less than 0, it would be unstable equilibrium. If df by dx it's a greater than 0, that means its slope is positive, it is the unstable equilibrium. Have you noted it down? Are you sure? Great. Now let's have a question over this. But let's suppose this is the graph of the force versus displacement, and this graph is something like this. They have mentioned 3 points. One of the point is A, another point it's a point B, another point it's a point C. So they want that which point represents stable equilibrium and which one represents unstable equilibrium. So which position represents the stable equilibrium and which one represents the unstable equilibrium? This is the case. Now when this kind of question arrives in front of you, you must look at the axis of the graph. Look at this is f versus x. So when graph of f versus x is given, when graph of f versus x is given, you are going to check the slope of this graph. That means you are going to check df by dx. So at one thing, df by dx at a, if I observe df by dx at a, this angle is the acute one, and that's why its slope is greater than 0. And when df by dx is greater than 0, this will represents the unstable equilibrium. This is as simple as that. Even from this you can have the conclusion that a is the position when potential energy of the system is maximum. I hope this is clear. Is it clear? Is it? Now let's look at the point C. This is the point C. If I make an angle over here, this is the theta, and as you can see that this theta is obtuse. If this is obtuse, df by dx is less than 0. df by dx is less than 0 at point C. At point C, df by dx is less than 0, and this represents the situation of stable equilibrium. Even this shows that potential energy at C will be maximum. I hope this is clear. Is it clear? And B shows no equilibrium. At location B, it shows this is the location of no equilibrium. Why? You can see the graph and came to the conclusion that B represents, with respect to position, maximum force. It represents the maximum force. I hope this is clear. So equilibrium means there should be no net force, and this represents a maximum force, so this could not be the position of equilibrium. I hope you understood this. Now let's understood that the question has been asked with the graph of u versus x, and that graph is something like this, and they ask that which one will represent, let's say they have denoted certain points. This is the location A, this is the location B, this is the location C, and they ask that which points represents which equilibrium positions, which points represents which equilibrium positions. So what you need to understood is, when equilibrium question is there, check with the graph labels. You need to check on the axis of the graph. This graph is of u versus x. This is for potential energy versus displacement. I hope this is clear. This is for the potential energy versus displacement. Yes. So when the u versus x is there, you need to take a snapshot. Let's have a look. It is something like this, and put it one of the object over here. Just try to displace it and check whether my object will coming to its initial position on its own. Yes, my answer would be no. So A is the position of unstable equilibrium. A is the position of unstable equilibrium. I hope this is clear. Now let's have a look. It is the point C. It is the case of point C. So this is the point C. Put up one of the object over here. Displace it slightly and just observe it. Will it come to its original position on its own? My answer would be yes. If my answer is yes, that means that means the location C represents a position of stable equilibrium. Is it clear? Is it clear? So does it crystal clear? Is it? Yes, you this things must be clear that you need to understand this are there are two kind of questions, or there are two kind of graphs could be there. One of them could be from u versus x, another could be from f versus x. If the question is from f versus x, what you need to do is just take a slope, think over it, whether it is greater than 0, whether it is less than 0. If it is greater than 0, it is the position of unstable equilibrium. If the slope is less than 0, it is the position of stable equilibrium. Next next if the graph is of u versus x, if the graph is of u versus x, put up an object at various locations and check that if I displace it from this point, will it come to its original position on its own? If answer to this question is yes, great. It has been it has been the position of stable equilibrium, because object can reach to its initial position on its own. And if answer to this question is no, then it would be an unstable equilibrium. It is as simple as that. Yes, do you understand this? Now let's look one more question based on stable, unstable and locations. Let's suppose the question is given that potential energy of a particle is given as u is equals to a by x to the power 12, sorry, x by 12 minus b divided by x to the power 6, where a and b are constants, where a and b are the constants, and and x represents position, x represents the positions. Find out value of x at which particle at which particle is in equilibrium. So go through the data once. Go through the data once. What they are talking about? They are talking about the potential energy of their particle, and that potential energy could be written in mathematical form as u is equals to a divided by x to the power 12 minus b divided by x to the power 6, where a and b are the constants and x represents position. You need to find out the value of an x at which particle is in equilibrium. So they want it is to be in equilibrium. For equilibrium, force should be 0. Do I have any relation which can relate F and U? Yes, I am having it. It's an F is equals to minus of du by dx, and when I say F is equals to minus of du by dx, I can have like this. It's F is equals to 0, that should be is equals to minus of du by dx. I simply differentiate this. I simply differentiate this and will get it done. So let's have a look. That u was a divided by x to the power 12 minus b divided by x to the power 6. What I want f, that should be is equals to minus of du by dx, and that should be equals to 0. So let's differentiate this. This is minus of d by dx of a into x to the power minus of 12 minus of b into x to the power minus of 6, and this should be a 0. So that should be 0 should be equals to a multiplied by to the power minus 12. This is 12 into x to the power, when I say x to the power n, it is n into x to the power n minus 1. So this is minus of 13. This is minus of b minus of 6 would be here. It's an x to the power minus of 7, and this would be equals to 0. This would be equals to 0. So if I try to solve this, it's a 12 into a into x to the power minus of 13 should be is equals to minus minus plus. So this is equals to 6 into b into x to the power minus of 7. I hope this is clear. Is it clear? Is it? So this is 12 into a divide by x to the power 13 should be equals to 6 into b divide by x to the power, this is 13, sorry, this is 13, this is 7. So that could be this 6 2s are 12. So it's a 2a by b, that is equals to x to the power 13 minus 7. So x to the power 6 should be equals to 2a by b, and that x could be equals to 2a by b to the power 1 by 6. This would be the answer. It is the location when your particle or when your system is in equilibrium. I hope this is clear. Is it clear? Is it? Great. So let's just wind it up this session over here. This is all about the conservative forces, non-conservative forces, and equilibrium. Please do remember this. Have a questions on based on this, and this will help us to gain good numbers. Thank you. Have a good day. Take care. Bye bye.